it's time for us to look at the fundamental theorem of calculus. And as the name suggests, it's a very important theorem. And what I'm going to do now is not prove the theorem, but kind of motivate the way we use it the way we do. The first part of the fundamental theorem that we're going to talk about is what I call the evaluation part of it. It's going to be a way that we can evaluate definite integrals. Let me show you what I'm talking about. Let's consider we have a problem like this. We have a unicycle. You're driving your unicycle at a constant velocity of 6 miles per hour between, and we want to know, well, how far do you travel between hour 2 and hour 8? Well, that's not a hard problem to calculate without calculus. You just take the distance or the velocity times the time you traveled at that velocity, right? So in this case, it would be 6 times 6, 36 miles. But let's go ahead and just look at it so that we can set up the fundamental theorem and how we work with that. So we've got the velocity at a constant 6 miles per hour right here. And let's suppose that this is time, this horizontal axis is time, and the vertical axis is velocity. And we're going from hour 2 to hour 8. Now let's think about this. For the first 8 hours, for the entire ride from 0 to 8 hours, we go 6 times 8. That's 48. 48 miles. Now, let's suppose that's not what we're asked for. We're asked from hour 2 to 8. So let's get the distance we travel for the first 2 hours and we'll subtract that. So the first 2 hours we're going 6 times 2. And we get 12. Now, this is kind of a roundabout way to do it, but if we put these together and say, well, then that means that from hour 2 to hour 8, we went 6 times 8 minus 6 times 2, that'd be 36 miles. Now let's look at this from the standpoint of a function here. Let's suppose we've got this velocity function, it's just constant. And let's do this, let's get the antiderivative, because remember, in the past when we've gotten position, if we had velocity, we integrated that. We got the antiderivative to get position. So I'm wanting to know the position, the distance from 0, from where I started. Where am I now? How many miles? And in fact, I want to know how many miles I travel from hour 2 to hour 8. So we got the antiderivative here. Notice, I've got velocity, I got the antiderivative. Now look at this. This is 6t. And t goes from 2 to 8. Well, notice this. If I put an 8 in here for t, I get this, which is the distance I travel between hour 0 and 8. And then if I come back and put a 2 in here, I get the distance I travel between 0 and 2. So I put these together, and notice I get 36, which is something we knew would happen, I mean, without calculus. But what we did was we calculate the area under this curve. See, it's 6 times 6. The time times the velocity would give me 36. There are 36 little squares in here. Well, what we just did was we evaluated this definite integral, the integral from 2 to 8 of 6, and we did so by finding the antiderivative of the 6 and then plugging in the 8 minus the plugging in of the 2. Okay, now notice that you might say, well, this is kind of a simple thing. Well, because it was just a horizontal line. We were just basically getting the area of a rectangle, a square in this case. But think about this. Even when we're calculating area under more curvy curves, right? We still view little rectangles as our starting point and let there be infinitely many of them. In other words, we take all these rectangles under the curve and we let their width go to 0. So what we can do here, we ought to be able to do to more fancy curves. Now let's suppose that I spice up the problem a little bit and you're riding your unicycle and you increase your velocity by 1 mile an hour. Every hour you travel, you increase your velocity by 1 mile per hour. And we want to find the distance you ride between hours 2 and 8. So let's look at the curve. So each hour, your velocity is increasing by 1. See, that corresponds to a slope of 1. See these little slopes of 1 here. So this is a graph of your velocity. You have time, velocity, and this is your velocity. And we want this between hour 2 and 8. Now let's think about the function here. This would not be v of t equals 6 like it was before. It would be v of t equals t. Now let's think about how far you would travel in the first 8 hours. Well, in the first 8 hours, what you're doing is you're getting the area under this triangle. Okay, you're getting the area of this triangle under this curve. See? So it's 1/2 base. The base is 8, and the height is 8 here, right? 1/2 base times height. That's the area of that triangle. So the distance between hour 0 and hour 8 would be 1/2 of 8 squared. Now what about the distance between hour 0 and 2? This little triangle right here. Well, that would be 1/2 2 squared. Now if you want just the area here, you would just take the big triangle minus the little triangle, right? See that? The big triangle minus the little triangle. Okay, now let's look at the antiderivative of v of t. Well, it's 1/2 t squared, just using the power rule for integration. Now dig this. I'm going from 2 to 8. So watch what I'm going to do. I'm going to take this 1/2, and in place of t, I'm going to put in an 8. That's this. That's the big triangle. And then I subtract 1/2. In place of t, I'm going to put a 2. See? That's this. See? And then you get 30. So the total distance you travel in this scenario is 30 miles. And that would be the area under the curve. And we could calculate this with this integral. Notice, we take the function that's in there. We get the antiderivative of it. See? 1/2 t squared. And then plug in the top bound minus plugging in the bottom bound. There it goes. Now, let's suppose we have this curve. And so now this is our velocity. So we've got time, we've got velocity, and this is our particular velocity. We certainly don't have a constant velocity. We're speeding up, we're slowing down. But if we wanted to calculate the total distance, we might say, well, if I want to go between 0, like we did before, between hour 2 and hour 8, I might just try doing little rectangles in there like we did when we first were introduced to the definite integral. And I get this change in time times this velocity, and I would get the little area of this rectangle. Well, if we do that for infinitely small little increments of time, what we're talking about is just using this definite integral. Just like we did with the first example where you had the constant velocity. So what we can do is this. To get that total distance, we can just integrate whatever this function is between 2 and 8. See? Like this. And we get the antiderivative, plug in the 8, minus the antiderivative, plugging in the 2. And that's how we could calculate that. And this is what the fundamental theorem of calculus tells us we can do when it comes to evaluating a definite integral. So let's look at an example. Let's suppose we have this definite integral. And we've got, x squared in here. And we know how to find the antiderivative of x squared. Because in evaluating this integral, this is the first thing I need to do. Find the antiderivative. So remember what we do is we take the 2 plus 1, 1 over 2 plus 1, x to the 2 plus 1. And I'm not going to need to put in the plus c here because this is a definite integral. I'm going to get an answer. I'm not looking for just a general antiderivative. But what we are going to do is we're going to say, okay, I'm going to evaluate this antiderivative from 1 to 2. Put a line there to indicate I'm going from 1 to 2. And here's what we have then. We have 1/3 x cubed from 1 to 2. Now, all I have to do now is put in the values. I have 1/3 2 cubed minus 1/3 times 1 cubed. And that, I just work this out and I'm done. And in particular, this one's going to be 8/3 minus 1/3, which would be 7/3. And that is the solution. That is the evaluation of this definite integral. And what we've just done there is we've calculated. If you looked at the graph and we went from 1 to 2, what we've just done is calculated the exact value of the area under that curve. That's what we've done there. Now, let's look at another one here. Let's suppose that we've got the integral of cosine x dx, and we want to go from 0 to, let's say, pi. Okay, from 0 to pi. Now, let's see what this is going to look like. The antiderivative of cosine is sine. Because if you differentiate sine, you get cosine. And we're going from 0 to pi. So let's see what that's going to look like. That's going to be sine pi minus sine 0. Look at this. Sine pi is 0, sine 0 is 0, so we just get 0. Now so what does that mean? Well, let's look at the graph of cosine from 0 to pi. Remember, the cosine graph looks like this. And this right here is pi. And this, of course, is 0. Notice what we did was we integrated it from 0 to pi over 2 here. And then we integrate it over here. Well, there is positive area here, negative area here, and in fact, they're opposites of each other. So if you look at just the area alone, this area here and this area are the same, but this is negative, so that gives us a 0. So sometimes your definite integral will give you 0 like that. But this is the way we evaluate these definite integrals. You find the antiderivative, plug in the top bound, minus plugging in the bottom bound.